Perfect. Hi, sorry for the difficulties. Hi, I'm Ferdous, and I'm here from Germany presenting the work on graph-based linear optimization for spatial-temporal population immunity calculation. And I'm sorry that I have to be here online. I didn't get my visa approved in time, so I could only attend virtually. Um,
Sorry,
all right.
you're really quiet. Would you mind speaking up or speaking right into your mic for us?
All right. I can try speaking louder.
Okay.
Sorry. All right. I'm sure after the COVID pandemic, we all know the importance of predicting the disease spread and how it can help us to find ways to prevent it. Um, sorry.
We can barely hear you. Can you try maybe increase your volume on that side, a volume output?
All right. Is it better now? Is it better? Sorry.
You're good.
All right. I'll go ahead. I'm not sure if it's better. All right. Perfect. Okay. Um, then. Um, yes, so here we will look at the how to calculate the immunity index caused by active immunity, so natural and vaccine-induced immunity for human airborne diseases. On the next slide, I'll focus on our showing our results with SARS-CoV-2 for Germany, but this can happen. This can be used for any other disease and also any other country or region. Um, Yes, so I will go through the challenges that we face and the solutions one by one and show the overarching result in the end. Um, so the first and the biggest challenge we had was dealing with the vaccination records and the data that we were receiving, since it was recorded independent of the residence location. We got the vaccinations based on where vaccinations were registered, and that comes from where they were administered. So in this case, for example, this is a map of Germany, and we have the different counties shown in different regions, and we see some locations, for example, here in the middle, where there's a vaccination level of 250% in comparison to the population in that region, which is obviously unrealistic. And the cause of it, we assume, is vaccination tourism, as there were vaccination hubs in the center, but not in surrounding areas. So people had to travel to get their vaccine. And how we dealt with that, or how we rebalanced the data, was by creating a linear optimization model, which would minimize the flow or the distance that the vaccine would travel to be rebalanced, and still make sure that every location has a vaccination below 100%. And we would do this for the last day where we have the data available, and make sure that it is percentually kept the same for all the past data. So we would see on the right where after the rebalancing, all the data has less than 100% vaccination, and it is still keeping the true data, the patterns are still there. The next challenge we've faced was taking into account the waning of the protection level of each vaccine. So we know that, for example, for SARS-CoV-2, in the first 14 days, the vaccination protection grows over time. and afterwards it wanes much slower than how it grows, obviously, but this needs to be taken into account. And we did this by creating buckets. So on the right, you can see that we, for example, create two buckets here. For the first 14 days, we put vaccines in the first level of immunity, so to say, and then move them to the next after 14 days, which are each given a different level of protection or immunity, depending on how good the vaccine is. And the extension of this challenge was also dealing with the different vaccine effectiveness and different vaccine sorts, which is the case for COVID, for example. And so that in reality, the buckets are not just two, there are many different buckets for different timelines and different vaccine types. And the next challenge we had was that the vaccination progression record was not coupled with the identity of people. So we didn't know if someone who's gotten the first vaccine on a certain day has received their second vaccine on another day, or if it was someone else who's received that second vaccine. And we had to make an assumption here, and the assumption that we made was that the person with the oldest vaccine is the one to receive the next vaccine. So here you can see with the buckets, when we know that 5 other people have received a second vaccine or booster, we would take them from the oldest bucket that we have and put those people with an updated protection level now. And the next challenge we faced was looking at recoveries from different virus variants, since we realized, especially with Omicron, how people who recovered from Alpha did not have the same amount of protection to Omicron, and vice versa. So we needed to look into how or which variant people got infected with. This wasn't available data that we could get, so we had to assume that people would get infected with the certain variants of concern in the area that is most active at the time. And then we look into how much immunity that variant provides against other variants in the future. And this is what we did, and we put everything together in the end. And this is the overarching result that we got. So just as an example, this plot here shows for Berlin and the 6 vaccines that were administered there. You can see with the curves, the number of, or the level of vaccines that each that were given for a certain time in Berlin, and immunity that is then caused by those and how it wanes over time, also leading to recoveries and so on. This is provided for every day, every county by the by our model, and it can be used as input for spatial temporal disease spread modeling, and also to look into plan pharmaceutical or non-pharmaceutical interventions by governments or organizations. And with that, I'm coming to an end. So thank you all for your attention. If you'd like to read more about our work, feel free to read the iClear workshop paper that we published last year. It's not the full work, but at least parts of it. And I'd like to thank my co-authors, Simon, Lucas, and Bernard, and our whole team, and the GLBIO ISCP team for the great conference here. I'm open to questions now here, but you can also email me or message me on Twitter.